Good afternoon, everyone. If you can hear my voice properly, can you just raise your hands from the dashboard? Okay. Okay. Good afternoon, everyone. Welcome to Midas Elite Training Series. I'm Bodhi Rudra from Midasoft, and today I will be presenting a webinar over modeling and analysis of a suspension bridge that will be following up from the last webinar that you attended. So the webinar will be more or less of about an hour or so. So I will be trying to cover most of the basic concepts that is needed for you guys to start with a suspension bridge modeling. So the agenda of today's webinar will be, I will be giving you an introduction to suspension bridges. Then we'll do different type of analysis. One is completed stage analysis, the construction stage analysis that is required for suspension bridges. Then we'll have a general overview of a project that I will be doing, and we'll do modeling and analysis for the suspension bridge. So let's start with the introduction of suspension bridges. So as you already know, that suspension bridge is something that is having a deck suspended by a cable. So if this is like a pylon, so we are having cables on both ends, and the deck is just suspended from the hangers. So it's a very complicated bridge because it has a lot of different displacements that you need to consider and other things. So to analyze such a kind of bridge, Midas provides you two types of analysis. One is completed state analysis and one is construction stage analysis. In the completed state, what you do is that you build a whole bridge on the basis of an initial state. The initial state is determined by the self-weight of the bridge. So in the completed state analysis, what you do is that you do an initial equilibrium analysis of the cables and then of the hanger using just the self-weight of the deck. So that is the initial state of the bridge. So from that self-weight, the program, what it does is that it will automatically determine the cable coordinates and the cable tension in order to sustain that self-weight load of that initial equilibrium state. So once you have gone through the initial equilibrium state, then we can modify the model and we can give some extra boundary conditions. You can do some other things, and then again you can do another set of uh, um, initial equilibrium state analysis to get the final cable coordinates and the tension forces inside the cables. Once you are done with that, the software generates the initial forces, that is the initial static forces for the cables, and then you can do a static analysis. Then you can do a static analysis for other live loads, for other loads like live loads and dead loads over that bridge. So that's why it is called linearized finite displacement method. This thing will be clear as we move on with the webinar today. The second way is the second step to the to suspension bridge analysis is to do a construction stage analysis. So construction stage analysis usually checks the structural stability during erection, and during erection there is a lot of large displacement because the hangers, because the cables, because the catenary actions of cables, there will be a large displacements that will be occurring, right? So we need to do large displacement analysis. So for doing large displacement analysis, we have to consider geometric nonlinearity. So for each stage, we have to consider the geometric nonlinearity in the construction stage analysis. And the deformed state will be then accompanied by the equilibrium forces that will be needed to achieve the deformations, achieve the large deformation analysis, large deformations. So this is a brief about completed state analysis and construction stage analysis. So we'll start with completed state analysis thing. So the steps required, as I told you before, that we have to create an initial model. Initial model will be having hangers and cables with the self weight of the bridge. So then when we do the analysis, the software will automatically generate the initial forces that are required to sustain that loading. So it will transform the loading, it will give you the coordinates of the cable, it will give you the cable tensions, and it will give you the initial forces that are required. Then we do other modifications that are needed, like we add boundary conditions, we add different kinds of all the structural modifications that we need, and then we perform the analysis again in order to optimize the initial forces that we got. So it will again change the cable coordinates and again further the modifications that you have done. Okay, so the initial equilibrium analysis, by this step I mean that we'll be doing it by wizard, and then once we do it by wizard, the software generates the initial forces. It will generate some initial forces based on the conditions that you have given in the wizard. Then we do the modifications that is needed, and then again we run the analysis. Again the software will generate another set of initial forces. Okay, so now once we have generated the initial forces and other things for the model that we need, now we can constrain the whole model as the final stage model, that is the completed model. That's why it is called completed stage analysis. And in the completed model, now all the nonlinearity that was there has already happened. So we just need a linear and a static analysis to be done. And what is the function of initial forces that we have got is that the initial forces will be just converted into the structural geometric stiffness to so that when the other loads are applied, those initial forces are also considered inside the analysis. Okay, so this will be the general procedure for initial completed state analysis. If you are doing manually, the whole bridge, like if you are not using the wizard for it, then you can just skip both these things and you can directly go for the third step. So you can directly go for the analysis instead of doing the wizard first and then doing analysis and then modifying and then again doing analysis. Okay. So the steps that are required that we'll be following in today's webinar is that we'll be first giving a material and section properties, then we'll be analyzing the initial equilibrium state using the wizard, then as I told you we'll do modifications, and then we'll perform another analysis to get the optimized results, and then we'll give the other loadings and we'll perform a completed state analysis. So this will be the general flow of the webinar that is there. Okay, so the bridge dimensions that that is being used, I will share you the tutorial after this webinar, that so I can follow step by step each and every things that I'm doing. Okay, so this is the general profile of the bridge that we'll be doing. So we'll go to midas civil. This is the general interface of midas civil. We'll start a new project. Okay, so we start by creating a material and section properties. So before that, you can change your units. If you wish to change your unit, you can go to TONF and meters. You can change your units directly from here. So you can change it anytime. Just make sure that you change it before you enter into a dialog box, because sometimes they forget that they have changed the units and they just give the dimensions or other inputs in units. They're thinking it's in wrong units. So you just have to be careful while changing units. So once this unit has been changed, every input that I'm giving right now will be in these units. So for material properties, I can either go to properties and material properties, or I can right click here, go to properties and material properties. So we can add a material property and start creating the material property. I hope that you guys have the basic knowledge of adding material property. So I will be skipping this portion. So what I will be doing now is that I will directly import the material property from a file that I've already got. Okay. So what this step shows is that if you have standard material properties and standard section properties that you are using again and again for your projects, then you can have a file with all the standard properties, material and section already saved in your hard drive. So whenever you are doing a project, you can directly import the material properties from there. So you don't have to create again and again. And import, while you are doing import, you can also modify the section property or material properties like that. Okay, so currently I'm importing all the material properties. All of them are user defined. It's not necessary to define a user defined material property. You could have gone to database and defined a steel section for cable state 2. Okay, so this is a user defined material property. So we have defined the modulus of velocity, the Poisson ratio and the weight density of cables for hangers, deck and pylon. What I want you to show is that currently you can find that for the deck I have given weight density as 0. So this is like 0 weight density. Why is it so? I will explain you in a bit. Okay, so just remember this. Then we'll go to section. So either you can go to properties, section properties, or there is a way to directly shift from material to section property. So I will just go to section and click on add. Okay, so to add a section you have to go again database and you have to input your data and all. I will directly import the section now. So I will import all the sections that are there. If you don't need anything, you can just click on that particular section and move it to the other side. So if you don't need anything, you can always do that in this way. Okay, so we'll just we need everything right now. Okay, so we'll just go to import and I'll click on OK. So it brings all the material properties and section properties inside the properties tab. Okay, so once you have done that, you go to you have to define all the or you have to define the wizard things right now, wizard inputs. Okay, so to go to wizard, what you have to do is you have to go to structure. You have to go to structure and there is a suspension bridge wizard option here. As I told you, this is not a necessary step to do it, but the wizard actually helps you to create an initial model in front of you. So it's not like it does everything, but it helps you create an initial model. It helps you to get the initial coordinates for the cables and other things. Okay, so for the wizard, I'll be using the inputs. Just a minute. So I will be giving the layout inputs based on the information that you are seeing here. Okay, so everything that is being inputted here, all the distances and the coordinates and everything is based on this diagram. So you can define your user input. Then for A1 it's 3.6 and for this it is 20.72. It's like 128.6. $60.8 and this is 328.6. This is 0 and 27. Okay, so this is for the layout information, and then the height. is 60.8. Okay, then we can just change these things. These are just given by default. So for main cable we are having cable section. For side cable it will be cable. For hangers it will be hanger and hanger, again hanger. Deck it will be deck. Pylon, pylon. Again cable section property, cable, hanger, hanger, pylon and pylon. No, deck, this will be deck and then pylon. Okay, so once you have done that, deck system, the width and that I'm giving is 11 mm. Okay, and I guess yeah, for the deck it is wrongly imported, so I will just give proper dimensions, so that's okay. Done. So once we have done it, so there's an option to add unit weight here, you can see, but we are not going to use this unit weight. So what we'll do is that we are going to use point load instead of unit weight. Okay, so what I'm trying to achieve from here is that if you see the slide properly, so currently what we are doing is that we are just setting up the geometry for the suspension bridge, and the loading will be applied to each hanger as a point load. Okay, so this will, what this will do is that it will create according to the different catenary actions of the cables and the truss actions and for the hangers. So it will have an initial equilibrium setup for the nodal loads, and it will automatically determine the coordinates for all these cables and the tension required to sustain that self weight. Okay, so this it will automatically, this the wizard will automatically do. So instead of giving unit weight, we are giving point load. So before doing the point load, I will just set hanger distance. So the hanger distance that we are giving is 10 at the rate 12.5. Okay, and for center, left means for both left and right it will be, because it's not an asymmetric bridge, it is symmetric bridge. So you just have to enter left, it will automatically enter for the right, and it will be like 32 at the rate 12.5 for the center. Okay, so you can see that I'm having 12.5 meter section between two hangers. Okay, so whatever loading that will be having that a hanger will be having will be for a 12.5 meter section. So you can calculate the for a 12.5 meter section using the deck properties. If you go to deck, so the area is around 0.5395. So if you multiply it with 12.5, you will, and with the density of the steel, you will get nearly about 52 point something. Okay, so when we are going to give the point loads, so what we have to do is that we have to give the point loads as 9 at the rate 52.9375, and this will be 31 at the rate 52.9375. Okay, so we are giving point loads for the hanger loadings. We click on OK. So once we have done that, then we have to define the shape of the deck. Okay, the shape of the deck. So we'll just check on shape of the deck, and the left slope is, so the left slope is, we can give it as 2.77 and the arc length as 650 meters. Okay, so you can click on drawing to see how your suspension bridge will look like. Okay, so once you have done with that, done with everything, then you can save the model, save the wizard file. It's always necessary to save it. I mean, it's always important to save it, because whenever you are using it in further projects, or if you have to modify a few things, you can just simply open the wizard file. So you can save the wizard file like that, and if you wish to open it, then you can just open the wizard file like this. Okay, so this is the way you can quickly do the things. Okay, so once you have done, once you are done with that, you click on OK. it will ask for saving right after you click on OK. That's because it's trying to analyze right now. So I will give some file name right now. So suspension bridge, it's the initial state. So initial equilibrium state. So I'm just giving it like that. Okay, so it will analyze the model and very quickly it will generate the whole bridge in front of you. Okay, and you can find that it has given both initial forces for large displacement and small displacements. Okay, so it has undergone both the things. So it has actually automatically decided the cable coordinates and the cable tension forces. Okay, so now what we need to do is that we need to optimize the bridge according to our needs. So if I have to do further modifications in the model, so what I will do is that I will go back to the hidden view. I'll go to the front view. So the modifications, like I don't want this node, so I can just select these nodes and merge it with the deck. So we'll go to translate. Okay, so in translate we can I don't want to copy it, I want to move it, so I will just click on move. Any box which is green in color is a dynamic box, so it can take the input from the menu inside, from the workspace inside. So currently if you don't know the distance between the two, you can use the help of dynamic box. So you can just click on the first node and click on the node where you want to move the node. So you can see that it creates an arrow. So if you click, it creates an arrow. So once you do that, it will automatically give you the distance. But since I don't need to translate it in y direction, I can just give 0. Okay. So I can click on intersect frame elements, apply. So it merged the node with the nodes there. So once you have done that, then you have to divide the element. I want to add more transverse pylon sections, so I will just select both the sections. Okay, so once you have the selection is not that visible, so I can go to display option and just give some random color, some different color that is visible. Okay, this is visible. So I will go to node element and I will divide the element now. You can either divide or you could have translated the nodes in the vertical direction. Both will give you the same result. Okay, so I can divide at an equal distance or unequal distance. So I can directly give divisions. So I want a division to be made at 1.25 meters, and I want a division to be made at 18.75 meters. So once you have done that, if you click on apply, you can see that it has created 2 more nodes. Basically it has created 4 more nodes because we have 2 portions of pylon. So once you have done that, I can go to front view and I can select both the pylons now and just activate these things. Okay, so I want to create elements in between. So what I can do is that I can go about creating the elements. So for creating elements, I have to go to node or element, click on create element, and I have to choose pylon for material properties, pylon transverse section for pylon transverse section properties. Again, a dynamic box. So I'll just click over it once. Whenever you see a box that is turning green, if you click, so that means it's dynamic box. So dynamic box, you have to be careful also because it takes input from the model that you're doing. Okay, so just click on it once to be sure, and then I create elements, and here too. Okay, then I select the elements. I don't want these 2 elements basically. So I can either magnify and select these and select these elements. So I can delete by pressing delete from the keyboard. Okay, so then I can just close this and activate the full bridge. So I can go to activate all. Okay, further modifications that are needed are for the boundary conditions. So I want a deck boundary condition too. I have not given any deck boundary condition right now. So I can go and select the deck and nodes. So go to the front view, select this node and the end nodes. These are the deck and nodes that are there. Okay, so I can go to boundary, go to define supports. So I can just fix all the translations. I will just release the moment at the ends. Okay, so I will give the deck and forces like deck and boundary conditions like that. Okay, so this is our boundary conditions right now. Okay, plus if you see the links between the hanger and the deck, that is given by rigid body links. So these are rigid body links. So this is connecting the link, this link is connecting the hanger to the deck by rigid body motion. So this is a master slave link. Okay, so if you have like self-anchored bridge, then in that case for the ends also you have to give a same kind of link. Okay, that's the only difference that is there. So once we have done this, like done given the support condition for the deck, I have to again give the support conditions for the deck and pylon connections. So I have to give different connections right now. Okay, so I will just undisplay the rigid links. Currently, the deck and pylon connection is in the way like isn't something like this. Show you. Okay. So the deck is not continuous over the pylon. So the moments are released for the deck and pylon connection here, and even the deck is now free to move in the horizontal direction. This is like the initial connection that will be there for the decks. Okay, so we have to release a moment here. We have to release moment here on both ends. Okay, we have to release moments on both ends, and we have to release translations basically on both ends. Okay. Also, currently the model, because this is again a model to get the initial forces, so we are just optimizing the model. So again, point of interest will be to give loading in such a way. So again, for this such a type of loading, I have to again simulate the deck connections in such a way. So the decks will be not connected to each other, the deck portions. So I have to give the beam and releases in such a way for the deck elements also. Okay, so I will go back to the model. So first I will just select the elements and select these elements for deck to pylon connections. Okay, and then I will go to, for beam and releases, you have to go to boundary and you have to go to beam and release option. So we'll click on beam and release, and currently I will be releasing both MY and MZ for it. Why MY and MZ? Because I don't want the deck connections too in between. So MY MZ, and also I'm releasing the FX force in this node. So I'll give ith and jth node. So what do you mean by ith and jth node is that for the elements that has been constructed in the directions, in this direction, this will be I end and this will be j end. Okay, so it's like that. So for the jth end, I'm releasing the translations and other things. Okay, so once you have done that, just select both the elements and click on apply. Okay, again select the pylon to deck connection on the right end. Okay, So you release moment on both ends, but this time it is the ith node that will be having transverse release. Okay, so once you have done that, you have to now simulate the deck releases, all the deck releases that are there. Now, usual practice for deck release is that you have, usually what I see people doing is that if you have two decks and you want to release the forces, all the forces, so they give uh, beam and releases on both ends. But it's not stable structure, right? You cannot give two hinges at one place. So so to simulate these things properly, what we can do is that currently if you just right click and display, so you'll find that the beam and releases are given in such a way. So already this node is having beam and release in this side. So what we can do is that we can start for the other deck ends, we can start by giving beam and releases on the ith end, and similarly for here, for these decks, I can start by giving beam and releases on the jth ends. Okay, so we'll do that only. So now we'll select the nodes that are there for the elements that we need to simulate the beam and release for. So you can select all the elements. So either you can select like this one by one, or you can directly type in the element number. So currently I will type in 204 to 211, and then 230 to 243, and press enter. So once you press enter, it will automatically select the elements that I have given the number for. I don't want the node, so I can just undisplay the node. Okay, so once you have done that, then you can go to beam and release and just release it in ith node. Okay, and click on apply. Okay, similarly for the other elements on this, or other deck elements on this side, I have to release it in, so I have to again type in the 228 and 246 to 253. Okay, so it's like on this, on the right ends. So once you have done that, you can just put my on jth end, release the my on jth end, and click on apply. Okay, so this is how you will do it. Okay, this step that I'm doing right now, it also explains you the manual methodology. Like if you are not following the wizard, then you will be doing exactly like this. Okay, so you will be, the wizard, what it does all these things in background. Okay, so you will be doing all these steps. So I need to create two groups basically. Why, I will explain you in a bit. So you create groups called nodes to be updated, and similarly a group for sag points. Okay, so you create a group like this. Okay, so once you create the two groups, you can close it. So now the nodes to be updated. Which nodes I have to update? I have to update the cable coordinates, right? I need to optimize the cable coordinates. So I will just select the cable coordinates. So if you are doing manually, you just give some cable coordinate. The program will automatically update it. So you can just go about selecting each cable coordinate that is there, or I can simply type in all the cable coordinates that are required. So like this, so I can just type in 2 to 10, 12 to 42, 44 to 52, 104 to, sorry, 114 to 144, and 146 to 154. So once you select everything, it will select all the cable coordinates that are there. Okay, and to assign the nodes to the group, what you can do is that you can just simply drag and drop the group over it. That's it. For the sag points are the points at the mid, right? Because these will be controlling the sag. So I will give the sag points as 27 and 129. Why there are two nodes? Again, because there are two sets of cables there. So I will just drag and drop sag points. So why do we require this group to be done? I will be telling you in a minute or so. So before analyzing things, we have to add self weight again at the hanger locations. So again, we'll go to works, and to add a self weight, what we have to do is that we have to first go to load, static loads, self weight. We already have a self weight defined. So instead of giving a default group, I can either create a group like this. So I can create an LG group for the self weight too, so that I can identify the self weight afterwards. So I can just select this self weight once, then go to LG and click on modifier. Okay. But you remember, initially while I was entering the properties, I told you that the deck has 0 weight density, right? So the self weight of the deck is not being considered right now in the model. So if you are like little tensed that if we add self weight as nodal loads, and if we add self weight like this, it will add it 2 times. It's not like that. So we have given the properties for the deck as 0. We have given the weight density for the self weight for the deck as 0. Okay. So in order to add the self weight over the hangers, what we need to do is that we need to give a nodal loads. So we'll just click on nodal loads. The load case be self weight, load group be the load group that we just created. And what will be FZ now? Initially, you remember for 12.5 meters of span between the hangers, we calculated it to be 52 point something, right? 9384. So currently, because there are 2 nodes shared by 2 hangers on each location, so we'll divide it by half. So we'll divide it by 2. Okay. So we'll give the FZ as minus 26.469. Why minus? Because it's in negative Z direction. So currently the coordinate system, this is X, this is Y, and this is Z. So the loading will be in negative Z direction. Okay. So we have to select all the hanger nodes. So we can go about selecting one by one. Again, I can just type in here 54, 202, 156 to 204. So once you have done that, once you have selected all the nodes, you have given the loading, just click on apply. So once you apply it, it shows all the loads over the structure. So once you're done with the initial setup that is there, so we can again so the manual way of doing things is that you have to go to analysis and you have to click on suspension bridge. So this is the suspension bridge analysis control, which is the same thing that the wizard does. Okay, so we'll give the number of iterations as 10 here, and analysis method as initial force, because we are trying to calculate the initial force. That's why we needed groups for nodes to be updated and sag points. So this node to be updated, we click on sag points. In case you have more constraints for the cable at the ends, like horizontal force, you're giving a jacking force or something, then you can give the horizontal force and consider that also for initial equilibrium analysis. Okay, and since we are considering the self weight as the loading over the to calculate the forces, so we'll be doing like this. Okay, so we'll click on OK and then perform analysis. Sorry. So it takes around 2.6 seconds to perform the analysis. So this what it does is that it generates the initial forces again, and these are like the final initial forces that you need. So these are optimized for the modifications that you have done. Okay. Apart from that, it also generates equilibrium element nodal forces. Okay. So I will go back to the presentation. I've given an explanation over it. So for the last, it generates two kinds of initial forces, as I was telling you before. One is your large displacement initial forces, and one is small displacement initial forces. The large displacement initial forces is something that is generated because of the nonlinear analysis that you have done. So what it does is that uh, it represents the equilibrium of the construction stage. So with the construction stage, whatever, if you are doing the construction stage analysis and you are doing large displacement analysis, so it will consider those initial forces inside the construction stage, and it will convert the forces into geometric stiffness, and whatever loading, extra loading that is required in order to sustain any deformations due to that initial forces will be supported by equilibrium element nodal force. Okay, that's why you are seeing two things in here. One is initial forces for geometric stiffness for large displacement, and another is equilibrium element nodal force. Okay, so those are nodal forces that are internally applied inside the software in order to sustain the equilibrium due to the initial forces. For the small displacement is something that is only related to construction stages. Sorry, it is only related to linear analysis. It is not related to construction stages. Okay, so the small displacement initial forces means it is not going to do non-linear analysis. It's simply static analysis. So for the completed state analysis model that I'm doing right now, it won't consider initial forces due to large displacement. It has no meaning for the completed state analysis. For the completed state analysis, it will only take the initial forces due to small displacement, and it will again increase the it will formulate the geometric stiffness for the initial force that has been given. Okay, so that is our whole ideology of doing the suspension bridge. So once we have got the initial forces, once we have got the model, so I can just fix all the boundary conditions in such a way that it represents the final model that will be there for the suspension bridge. Okay, so finally I won't be having all these boundary conditions, right? So if you just go to boundaries, so I won't be having the beam and releases for the deck. The deck will be connected now. So what I can do is that I can just delete these beam and releases. Okay, so I will just click on delete from keyboard, double click on type 3 and delete it. Okay, so I will have deck and pylon connections. For clarity, I will just undisplay the loading, but again this end release has to be released, has to be fixed now. Okay, so what I will do is that I will just right click over the beam and release, go to properties, and I will just uncheck MY release for these, and for the other ends I'll just uncheck MY release for the other ends. Okay, so once you are done with that, for the you have to sustain the cables now in horizontal directions. You have to restrain any forces for the cables in the horizontal directions. So you need a stay boundary conditions in here. So for that, for the sag points, so for that what we can do is that we can go to boundary and we can go to elastic links. Okay, from general I can go to sorry, I have to give general. So SDZ means I have to give an elastic link in this direction. So SDZ will be actually in global X stiffness. So I'm going to give very high stiffness for global X, and I'll just copy the link on the other end of the span 2. For the two nodes, again it turns green as you can see here. So it will take, sorry, so it will take the input from the sorry, so I can just type in also here. So 2778 and click on apply. Sorry, and you have to give in Y direction. See, if it doesn't find any node at 11 meters, it gives an error. Okay, so you have to give in a Y direction. So once you have done that, it generates two elastic links. Okay, for the sag points. So that this will be like central span stay. So it will just inhibit any movement of the span of the cable in the X directions at the center span. Okay, so once you have done that, I need to apply other load cases now, because this is my completed model now. This is how my model will be will look at the final stage. Okay, so I need to apply other loads. So for other loads like slave loads and things, so I can go to static loads. You can always give live loads, but for now I'm just giving some basic static loads. So I can define a user defined static load. Okay, and then I can define the loadings. So again, you have to go to nodal loads. So these are like very simple static loads, just to show you how to do it. So I can choose LC1, and for the nodes I can just choose 231. Okay, so this is the center, at the center. So this is one static load. Then LC2, I'm giving it at node 223, and LC3 load case I'm giving 46 ton force at 210. Okay, so just press enter and apply. So you can find that all the loadings has been given here. So this is for LC3, this is for LC2, and this is for LC1. Apart from that, we have also got the self-weight that are there. Okay, so this is like all the loads that will be there. So for all these loadings, for self-weight now and all these loadings, it will do a simple linear analysis, because all the nonlinear effect that was there before has already been considered using the initial forces, right? So we don't need the nonlinear analysis now, so we can just delete it. We can delete the suspension bridge data too. So once you have done that, you can go to analysis and perform the analysis. Okay, so now once you have performed the analysis, you can check different results. You can go to deformations, deform state for the load case LC1. So if you need a tree menu too, because this usually occupies the tree menu, this menu will occupy the tree menu usually. So you can right click over this black portion and go to tree menu 2. Okay, so I can just display the LC1 load case, which is this, and click on apply. Okay, and I can also check the undeformed positions. So I will just check on undeformed. So it shows in a very thin line. It is a little hard to see. So you can see the very thin line for the undeformed position, and you can go to legend, click on apply. So this will give you the deformations, the maximum deformation, the minimum deformation at what node. Like for 180 I'm getting the maximum, for 1 I'm getting the minimum. So that way it will show you. Okay, similarly you can see the result tables, displacement tables. So for displacement tables, either you can go to result tables and displacement. This is one way to go about it. Or what you can do is that for any table basically in the results, there is a small tool besides the deformed shape, or besides the first box that is there. You can click over that. So I can choose the nodes that I have given for loading. Okay, and I can select all the load case, and click on OK. So it will give you the displacements for those load cases. For bending moments, what you have to do is that I will go to undeformed, I'll go to forces, beam forces and moments. So beam diagrams, basically I have to go to beam diagrams. So either you can go from here or here. So choose MY, I'll uncheck deform, click on apply. So it shows you the bending moment diagram now, okay, for this loading. For cable forces that is there, so you can go to truss forces, LC1, and click on values or apply. So it will give you the cable forces now. But the thing is that if you go to tables like truss forces, I can choose only cables, right? So I can choose the material, and I can just click on cables and replace it. So these will select only the cables. And if you select LC1 right now only for the cables, okay, and click on OK, so you'll find that 47, 46. So this is something that is a cable force additional to the initial force that was there. Okay, the initial force that was generated by the previous analysis, if you go there and go to tables, you'll find these axial forces have been already generated inside the cables. Okay, so in addition to it, whatever forces that are there due to the load case LC1 will be these forces. So the total cable force will be actually that and plus that. Okay, I mean the initial force plus the force that you're seeing right now. Okay, so once you have done that, like for the initial force and if you wish to see the total force together, so what you can do is that you can go to load, static loads, go to initial forces, go to small displacements. So there is an option called initial force control data. Okay, so in here you can add initial force to the element force, and you can choose the load case to which you want to add. So it will add those initial forces and it will show you the total forces for the cables. Okay, so this is how you will be doing if you are doing this is how you will be doing the completed state analysis. So this is just one part of the things. The next portion will be to do construction stage analysis. Okay, the suspension bridge is just a minute. This the 180 that you are seeing, you have asked a question about deflection. This is not a deflection, this is the node number over which you are seeing the deflection. Okay, so don't confuse it with the deflection. This 180 is the 180 node number. So if you just go to 180 and press enter, so this is the node which is having the maximum displacement. Okay, so maximum displacement value is something which you can see it here. It's like 0.3 or 0.3 Z. It's at 180 node. It's okay. It's like 0.3 meters something. Okay. So I'll come back to your questions afterwards, because it's a long webinar. It's a lot of things to cover in one webinar. So I will just cover all the things, and I will come back to your questions afterwards. Okay. So sorry for that. We'll continue with the webinar. So currently we'll be doing the construction stage analysis. Now by construction stage analysis, usually you will be thinking that we are doing stage analysis one by one with stage, right? First stage we are having pylons, then the second stage we are having deck, the deck is being constructed one by one. So all these things has to be done one by one, right? So, but the thing about construction stage and suspension bridge is that we have to check for different how the forces are being redistributed to the beginning. Okay, so we have the completed state model already with us. So we go by backward construction stages. Okay, so backward means that currently I have the rigid connections between all the decks and the pylon ends here, right? So I will just remove all those rigid constraints again to give a pin constraint, and then I will start removing the cable hangers one by one. Okay, so then I will start removing the hangers one by one and the deck one by one. Okay, and finally I will have just the initial model that is there. Okay, so this is the reverse philosophy of doing it. So we use a reverse construction stage, like or also called backward construction stage. But during the erection of the structure, cable state, a suspension bridge undergoes a huge amount of deflection. Okay, so in that case we need to consider large displacement analysis or geometric nonlinear analysis instead of linear finite displacement analysis. Okay, so I won't be using the initial forces for small displacement. That will be totally disregarded in this case. Okay, so it won't be used for any load cases that has been defined in construction stage. Okay, the only initial forces that are defined for large displacements will be used. Okay, so this is the way the construction stage is being staged out. So for stage 1 we are having the whole structure, and we are having the boundary conditions that is there for the completed state model. In CS1 we'll reactivate the pin connection that between the decks that we gave. You remember we gave pin connection between the decks, so we'll reactivate those pin connections, and we'll deactivate the stay because the stay wasn't there, it wasn't fixed beforehand. Okay, and after that we'll just remove structure groups one by one. So this is how we'll be defining our construction stage. So we'll have stages, we'll define stages, we'll have groups, okay, and we'll be activating and deactivating things inside the software. Okay, so we'll go back to the model. So now we'll save this model as, instead of initial years we'll just say construction stage now. Okay, so now we start by defining the construction stages. So the different construction stages that are there, I will go to load, and then I will go to construction stage and define construction stage. You can either do all this thing or just go to this small icon that is always present in front of you in the workspace. So you can define, you can just click on that icon, it will bring out, it will pop out the construction stage input box. And then you can either go by adding one by one each stage, or what I can do is that I can click on generate, I can type a name as CS, and since I want 8 construction stages, so I will just click on, just name it as 0 to 7. Duration is something that is needed if you are including the time dependent material properties. Okay, so and at that time it becomes very important, duration thing, but I'm not touching that aspect right now, so I will just give it 0. I will save the result for each stage. I need the result for each stage. Additional steps is required if you are, if inside a construction stage you are applying loads at different days. Okay, so you are doing like 2-stage pre-stressing inside one construction stage, then you need additional steps. Okay, you can check on additional steps for that. So click on OK, so it generates 8 construction stages right now. Second thing that I was telling you is to define groups. So for groups you have to go to groups and go for structure groups. I will just click on, right click on structure group, go to new ... Okay, then I will type in SG for name, and for suffix I will type 0 or 227. Okay, so I'm not having 1. Why? Because this is just a naming for naming ease. Basically SG0 means it will be activated in CS0. Okay, so it means something like that. So I don't have any structure being activated, deactivated, or I'm not having any structure activation, deactivation there. Okay, so I'm not having any SG1 group here. Okay, so I will just give groups in the name or in the order that I'm having the construction stages. Once I have done that, I can go and assign the structure group. Okay, so currently for the SG0 I'm having the completed model, so I'll select everything in the structure and just drag and drop SG0. Okay, so SG2 is something that is having only the elements for the first construction stage. Okay, so first construction stage, so we'll just select the elements in this manner. And we'll give SG2. So once you give SG2, you can inactivate it and see how it will look without that structure. So I have already got a model where I have done all these things. So I will just open a model. So just open a project model. So in this case, I've already given all the groups. So this is like SD3 data. So if you inactivate for the SD3, then this is like SD4. If you inactivate that, inactivate. Okay. And SD6 if you inactivate, SD7 if you inactivate. So if once you inactivate all those things, you will find that all the deck elements have gone. Okay. Similarly for boundary groups. Now for boundary groups, you have to have a BG boundary group. If you remember. So if you just right click over boundary group and go to new dot dot dot. So I have defined 3 boundary groups right now. One is pin connection, one is BZ, and one is stay. Okay. So for the BZ boundary group, what I'm doing is that I'm giving the completed state boundary group. So what you will do is that you will select all the structure, the overall structure, and just drag and drop BZ. Okay. So once you have done that, so just select everything because we need all the boundary conditions in this, and then click on OK. So this is BZ boundary group. For the stay, I have to select the nodes at the stay. Okay, the nodes at the stay that is having the elastic link, if you remember, for the horizontal constraint. So I can just drag and drop stay for the elastic links. Okay, and for the pin connections is something that I have to give afterwards, right? In the stage where I'm giving again getting the deck unconnected to each other, so I have to activate pin connections. So I have to define the pin connections again like before. So again we give beam and releases like before. We give beam and releases for the pin connections, and we define the pin connection group to it. So how do you define the group? So you simply have to select the whole structure and drag and drop pin connections. Just uncheck all the other load cases except beam and release. Okay, so it will choose the beam and release, all the beam and releases that you have done in the pin connection group. Okay, so once you have done, once you have given the groups and other things inside, so what you can do is that for the loadings, you can go to load, static load cases. Okay, so I've removed all the other load cases because those were non-construction stage loads. And for the self weight, you have to give the type as construction stage load. What this will do is that then the self weight will be run only for the construction stage. It won't run a static analysis for self weight. Okay, so it just excludes. This is like an exclusive construction stage load. Okay, so you can go there and make the type as construction stage load. So once you have done that, you have to define construction stage. So what you do is that for the first construction stage, you just double click on it and you add SG0 in the first stage. because we are adding the full stage for the completed stage model here. For the boundaries, we are having BG and stay, so we'll select BG and stay and add it in the activation menu. So we have activation and deactivation menu, so you have to select the particular boundary and activate it if you wish to activate it, and then click on apply. For stage 1, we are not having any structure group, right? You remember? I don't have any structure group, but the only thing is that in the boundary condition, the pin condition connections will be activated now, and the stay that was there for the for the stay nodes, for the sag points, I will deactivate those things. Okay. And then if we start removing the elements, so CS2, when we are doing it, we are removing SC2. So you see a factor called redistribution. So when we are removing a particular element, it should redistribute the force that the element was carrying into the whole structure, right? So we are redistributing that force 100% to the structure. So similarly, if we go to CS3, you go to CS4, we'll deactivate the elements one by one. Once you have done all these things, you can just check on, go to works here, just check on the things here. So from base, I can go to CS0. So the CS0 is having only 4 beam and releases. That is the completed state model, okay, and it is only having the self weight that is there. Then CS1, it will activate all the beam and releases deck and between the decks. CS2, it will deactivate the elements. Then you can use scroll from your keyboard to go to the other stages. Okay, so once you have done that, once you have done this thing, then for the next step, it will be to define the construction stage analysis control. So we need to define we need to add we need to have some nonlinear data in it. So we have to go to analysis and we have to go to construction stage. Okay. So for the construction stage analysis control, so for the construction stage analysis control, you can find that the last stage, we have the final stage is the last stage, and then we include the nonlinear analysis, and we include equilibrium element nodal forces. Okay, so it has already calculated the equilibrium element nodal forces once we have done the suspension bridge analysis. So we'll be using those equilibrium element nodal forces in each stage, and it will do a nonlinear analysis for each stage. You can configure the nonlinear analysis control using the number of load steps. So you can give a number of load steps in here. You can give the maximum number of iterations per load step and other things. Okay. Accumulative stage is something that it accumulates the nonlinear analysis is not dependent on each stage. It is accumulating all the results that is there for each stage. Okay, so that is something that is needed when you are doing a forward stage analysis. Since we are doing backward stage analysis, independent stage will suffice us. Okay, so once we have done, once we have given the nonlinear analysis control, we just click on OK. Okay, and then we perform the analysis. So once you perform the analysis, it will directly show you the last, in the post-CS stage, post-CS means after construction stage, will directly show you the first stage model, because that was the last stage model that was there. So what we do is that we go to CS summation, CS7, deformation, deformed shape. So we choose the stage as CS7, we choose the load case as CS summation, and then we click on deformed, we just give a scale factor as 0.2 or something, and undeformed shape. So this will be something like that, the undeformed and deformed shape that is there. Okay, then we wish to see how the sag point is behaving in each stage, how it has behaved in each stage. Okay, so what we'll do is that we'll go to results, and we'll go to stage step graph. Stage or step graph that is there. So we'll click on stage or step graph. Okay, then we'll add a new function, or I already have function. So once you add a new function, you just choose the sag point in the structure. That was 27th node. So you can go to 27th node. So I'm choosing this node right now. Okay, so I'm giving components at DZ, so it will monitor the displacements that are there in Z directions for 27th node with each stage. So if you check on sag and click on graph, so it will give you a graph with stage. So this is like the completed state. So this is at the end, it is completed state. Sorry. Okay, and this was the initial state. So you can find that, you can easily see that in the completed state, the stack point had 0 deformations. So initially it had a deformation, it had some deformation. So using and with the construction stages, it reduces to 0. So this is what backward analysis does. Okay. Similarly, you can have other things like the setback values. Now for a construction stage, setback value is something that is very important, because initially in the final stage model you have a fixed sag length, that is this. So in order to have 0 moments in the pylon, what the software automatically does is that it gives a horizontal force to reduce that moment to 0. Okay, so it gives an equivalent horizontal force to reduce that moment. So in order to do that, in the actual structure, we give a setback to the pylon. So once all the loading is done, it comes to the straight position and it comes to a vertical position. So this setback can be actually found out in the model. So if you go to like CS7, deformation, deformed shape, go to DX. Okay, you go to undeformed. So this is like the undeformed and deformed shape. Also, you can check on for a pylon node, you can check on stage step graph. Okay, so you can give a DX component. Now I can monitor the DX displacement for the node that was there. You can just check on right tower for the name and for the control of this node, and just click on graph. So once you click on graph, this is the top of the tower. This is how the top of the tower is behaving. So initially it had this much of a deformation from 0, and then it sets back and it comes back to 0 in the completed state model. Okay, you can have other, you can also review the moments that are there. So you can go to forces, beam forces and moments, and see the moments that are there. Okay, so if you go to CS0, so this is about the completed state model. So if you go to legend, so you can find that this is what we want to achieve. So we want to achieve 0 deck moment, nearly 0 deck moment. So it is nearly 0 for the deck right now. Okay, and during the construction stages, during the erection procedures, you have moments in the pylons. So those moments are being shown here. You can also see the variation of axial forces in the pylon and in the cables with the stages. Okay, so again for those things you have to go to stage step graph, and you have to add a function of thrust or force for the cables. Okay, and then give the cable number and the element number and the node position where you want the result to be monitored. And for the tower also, you have to define a beam force or stress, and you have to define the force, axial force in the tower. So once you do that, you just check on both the things and click on graph. So you get the tower axial force and the cable force This is how it is gaining the forces, the axial forces. Okay, so this is in short how you can do a suspension bridge and review the results for the suspension bridge. I'll give you the tutorial for it. So this whole webinar has been started directly from the tutorial, so you can follow each and every step in the tutorial that is there. And if you need any explanation on any step, you can always reach us to us. You can always reach us. So you can always reach us to ts@midascity.com for any further queries and doubts. So I'll be taking few questions right now, since we have a fair bit of time. Okay, so in case you have any more questions, like I have one question from Mr. Dong regarding permanent load cases. What is the difference between permanent load case, transient load case, and all cases? It's just nomenclature that the software follows. It's nothing special. So it's just like there are some load cases that are defined as transient, like these will be like centrifugal force, braking force, wave pressure, wind forces. They are like transient. These are not. These are for a limited amount of time, like earthquakes, right? So this is just a classification that the software follows. It's nothing else. So permanent load cases is something that will always be there, like dead load, live load, right? So, and all load cases is considering all the load cases. Okay, if you have any other queries on the suspension bridge things that we have done, so if you have any other queries, you can always mail us to ts@midascity.com. So I know it was a bit too much for a webinar, but I hope that if you see the webinar again, we will be sharing you the videos and other things. So if you have like all the webinars, if you want to see the webinar again, you can visit, you can see the webinar yourself. And in that case, if you have any other doubts, you can always reach us at ts@midascity.com. Okay. Yeah, I will be sharing you the video, sir. So anyways, you will be getting all those things. So you can look at at ease all the boundary conditions that I've used and everything. So we'll be sharing you the video. We'll be sharing you the tutorial that I have followed. Okay. So all the material will be given to you. Okay. So thank you so much. Thank you for attending our webinar. I'll be answering all other queries that are there over the mail. So I will be answering all your queries, and hope you join the other webinars too. And thank you for attending the suspension bridge webinar. Thank you so much.